Yeah, they would be sitting hung up in a barn for the last 25 years ago.
Well, looks like it's the official time. Welcome back, everyone. Any questions at all before we get started, folks? Okay, well, we're at a pretty pivotal part of the class so far. With where we're at in Moodle, this is what we have to get through. We'll do our third exam on Tuesday. Thursday, we'll still have class right before the break, but it won't be like an exam class, so it'll be a lot less stakes than normal. Then we'll have an entire week off. I think for a lot of people, that's a good week to get caught up. I hope you're able to take some time to not work at all. That'd be ideal, I think. After that, it'll be a couple more weeks to get through, and then the finals week. I'll be posting some extra information here about the final exam, review problems for the final exam, old final exams, a bunch of things like that. As we get closer to that date, I'll probably start propagating right around Thanksgiving break or towards the end of it. So we're very, very nearly done with all the topics. Currently, we're in section, let's see, 6.3, and we only go to section 6.7. So Thursday, we'll be working on section 6.4, and when we come back after the break, we're just finishing off the last few topics and then reviewing for the final exam. So congratulations, we're definitely over the hump at this point. We just have to get through that third exam. So we'll finish a couple topics in 6.3. That set of notes is very, very nearly done. Then we'll be doing these review problems here. We may not finish every single one of them, but we'll get as far as we can. And for whatever ones we leave on the table there, they will get solved. So if you come back here, you'll see the solutions to every one of those. Then this is the review problems for the book. This one here is just blank lecture notes. You can treat as worksheets again. And this is just a whole brand new sample exam problems. I think this one is 23 questions long, so way longer than a real exam, but it gives you lots of extra opportunities to practice each one of these topics. I don't have solutions on these at all. I have to actually solve them, and I plan to have them solved and uploaded sometime Sunday, probably around the afternoon earlier. So that's our plan so far. Any questions at all, folks, or comments at the moment? Okay, well, let's go back to section 6.3, figure out what we have left to do there, and then we'll start reviewing in our next document. So 6.3, we defined a logarithmic function finally. If you have something of the form b to the x, it's a invertible function, and its inverse would be denoted this way. It takes the same base, and we write log base b of x. Swapping around the domains, the logarithm will always have a domain 0 to infinity, unless we transform that function. So in green, that's our nice logarithm right here as a graph. We'll always have a vertical asymptote as opposed to the exponential function having a horizontal one. And it definitely reflects across y equals x, so it looks like a true inverse function. Then with that knowledge, the big part of the notes was really right here, this table. If you take an equation in exponential form, you can now translate it to an equivalent equation in logarithmic form. They'll have the exact same solution set. But sometimes you want to be in logarithmic form to solve your equations. Other times you need to be in exponential form. So when we were solving equations, coming down in example 3, we definitely need a calculator, so that's some information on how we did some of those computations. Or that was example 4 finally. Then example 4, we try to solve this equation that we stated quite a while ago in the notes. All we had to do is take the exponential equation, write it down as a log base 2 equation. Then we did kind of cheat a little. We looked at the change of base formula in that format just to see what x would approximate as. But the good news is that is the exact solution to that equation, 2 to the power of x equals 10. Now we'll solve a couple more and start reviewing. Any questions at all, folks, on our solution on part A? Okay, this section 6.3 is probably going to be one of the shorter sections in ALEKS, I would say. It doesn't have a ton of stuff going on in there. But the major concept is still definitely this. If you have this down pat as you get out of section 6.3, then you're doing really well in this chapter so far. So let's practice this a couple more times on our part B right here. It says just solve for x. And if you've seen logarithms before, you could probably stare at that and say, I know what x is. Anyone happen to know what it might be? It is e, good call. So this one has an immediate solution, x is e. Now our goal is to find it. So here's what the steps are going to be. Once we solve it though, that's a good tiny little mathematical fact to be aware of with this equation here. Now the first problem is they didn't give us a typical logarithm. This is the natural log. So what I would do is rewrite it in its more standardized form. I want to show what the base actually is. So natural log of x really means log base e of x is equal to 1. Then when you stare at this equation, it becomes a little bit more clear, but not perfectly clear what the solution should be. But let's take a look at just this part. The logarithmic part is telling us that the exponent needed for e in order to obtain x. So that's the exponent we need to have on our e right there in order to obtain x. The exponent was definitely a 1. So e to the power of 1 would be your x, is what this is saying. These kinds of things are sometimes handy because a logarithm is always an exponent, but that's kind of confusing to me every time I write it out. I have to think about it and see if I can convince myself it's true. Way easier to just take that equation and put it in its exponential form. It's massively more clear if you do that. So recopy the base, here it is. We're dealing with the inverse function, so this will be e to a power equals something on the right-hand side, and we just swap things around. The power that goes here was the output of the logarithmic equation. It's now input of the exponential equation, and the x, which was input to the logarithm, is now output to the exponential. So we've automatically solved it just by transforming its form, and our solution is x equals e. So we got it, folks. The only way that's true is if you put exactly e right there for x and you have a true equation. Any questions or comments on solving that one? Okay, there might be a couple equations like this on our upcoming exam 3. These are the last set of notes on our official third exam, but it's pretty much just going to be like this, where the moment you put it in one form or the other, you're basically done. So let's try that one more time. This equation, in all honesty, is really kind of bizarre. I don't know what kind of word problem would ever lead to something like this, but as a mathematical object, it's fair game as an equation, so let's solve that one as well. What makes this one weird is now x is the base. So we'll take this, rewrite it in this format. X to a power of 3 becomes our exponent, is going to be equal to 7. Well, this one is a multi-step equation. Well, I guess the last one kind of was. We simplified the power of 1 on e right here. But here, to solve for x, just take the cube root of both sides. Step would look like this on paper. Cube root of the left-hand side, cube root of the right-hand side. The cube root is an inverse function to the cubing function. And so you could visualize the next step like this. You've just canceled out power 3 on your x. X is freed up, and so now x equals the cube root of 7. So part C is probably the least useful equation on there in all honesty, but the whole point of all of these, just practicing going from logarithmic to an exponential form so we can solve an equation. Well, any other questions, folks, on these last two problems here? Okay, we've done it then. This is the fastest we've ever closed out a section, about 9 minutes into class, but wasn't too much left on there. So let's save this, and now we're going back to section 5.5, reviewing for our third exam. So we are on this document right here, Formulas and Concepts on exam 3. Let me open it up from here. The way this document is organized is, it's just mentioning the massive theorems and ideas that we want to be aware of to be successful on the third exam. And for every one of these concepts, there's a really fast example right down below. I forgot to put enough white space on this. Sorry about that. If you printed this out, you might need additional scratch paper as we solve through here. So let's solve these one at a time. We're starting off at the very first section, and that's probably a good idea because we left this polynomial theory stuff for our third exam. It starts off by saying if a polynomial is divided by x minus k, the remainder is f of k. So we're looking at the remainder theorem, and honestly, it's a pretty fast problem. It'll always give you a hint that you're using that theorem. If you see use the remainder theorem to evaluate, this is what I would do immediately as per reading those instructions. I'd probably put at the very bottom p negative 3 equals. This is just a reminder that we have to give that conclusion, what the overall answer is going to be. Then we convert the whole problem into synthetic division. Negative 3 copies in here. Then over here, we'll copy in coefficients. Let's double check. Power 4, 3, 2. We're missing power 1, so we'll throw in a 0. There'll be negative 1, negative 2, 4, then 0 for our x term, and minus 3. My checka is usually if it's a power 4, you should have one more, 5 different coefficients inside there. Then drop a bar. And now we're back into the land of synthetic division. It's extremely fast, but if you did ordinary division, you still get the same result. First thing that happens is negative 1 copies down. Then the negative 3 is going to multiply that result, giving us a positive 3, and then just repeat that pattern. Only difference in this next step is you add up the two numbers you see right here. So now we're at a positive 1, multiplied by negative 3. Now we're at negative 3. Still a positive 1 when we add up this column. And it feels redundant, multiplied by negative 3, negative 3 again. But it's good to be methodical, even if it feels kind of robotic almost. Now 0 minus 3 is negative 3. We're multiplying that by negative 3 again to get a positive 9. The difference here is 6. And this is the danger of the remainder theorem. Once we get to this step, it's extremely tempting to just end your problem just like that. But that's not quite the answer to this. The answer is to evaluate p at negative 3. So the last thing you have to say is p at negative 3, it's the remainder, and it's now 6. So that one goes really, really fast. The remainder theorem is kind of nice when you see this one on exams. It's not too bad to get through, but we just have to be familiar with it to know what's going on in that problem. Any questions, folks, on finishing off that one there? Okay, next easiest theorem would be the factor theorem. It's not too bad to use, but it feels, I think, a little bit more confusing when you see it as compared to the remainder theorem. The factor theorem says, if the number k is a 0 of f of x, that will happen if and only if x minus k is a factor of f of x. But if it's a factor of f of x, then f at that value would be equal to 0. So on one hand, you have at 0 here. Other hand, you have a factor, but those go together. If you factor something, you found a 0, essentially is what this is saying. So now here it's saying, use the factor theorem, and I'll use the same kind of language here, so you'll know which theorem you're probably using on the problem. Use the factor theorem to determine whether x minus 3 is a factor of p of x. So here's what we have to check. We want to take p of not the negative 3, we'll take the opposite value and put in a positive 3. And that's pretty much what this is saying. If k is a 0, then x minus k is a factor. We are always dealing with opposites. So we need to show that this thing equals 0. If it's 0, we'll say, yes, it's a factor. If it's not, we'll say, no, x minus 3 is not a factor. So back over here, at this stage, we're just using the remainder theorem and seeing if the remainder is 0. Divide x minus 3 into this, and you'll get a 3 here. We always put the opposite of that, or just copy what's inside the function when we go to the synthetic division. Much like the negative 3 here, copied as a negative 3 up here. You know, that's probably a good thing to tie together. Then back over here, this is power 3 with 4 different coefficients, so we can just write them in. It'll go 2, negative 4, negative 4, 9. And here's our second run of synthetic division. Copy the 2 down, then multiply by 3, giving us a 6. Then over here, add them together, we get a positive 2. Multiply by 3 again, and we get 6 again. then another positive 2 in this location. But now when we multiply by 3, we get 6, tally that, and we're at 15. But the conclusion is not done until we come back and write out this. P of 3 equals 15, since P of 3 is not 0, x minus 3 is not a factor of P of x. So that's the use of the factor theorem on this one, where it didn't work out. It wasn't even a factor. Pretty fast to check, but any questions, folks, on this one? Okay, let's try a second one right here. The factor theorem is, again, kind of a confusing one because sometimes the problems are asking us to do a little bit more. I can't ask every single one of these examples on a real exam, so I just want to put that out there right away. When I write exam 3, what I'm doing is I'm going through all the material, like say this document. I'm only going to take a representative selection of these kinds of problems and concepts. I can't put every single one on the exam. That's more like a 2-hour exam at that point. So if I choose example 3, I have to make the rest of the exam shorter to account for that one. This one's the longer one. Let's see what is happening on this thing. For the polynomial g of x equals x cubed plus 2x squared plus 5x minus 26, it is known that 2 is a 0. So if we do the synthetic division with the 2 here and the right coefficients, we should get 0 right there, which means we can factor this thing by dividing by x minus 2. But we need to use this information to express g of x as a product of linear factors. So folks might remember this one from ALEKS. This was the really tough one in ALEKS, I think. So to solve this, let's start by saying, since we know that 2 is a 0, we can say g of 2 equals 0. Now we're going to take g of x and go x minus 2 times something else. We'll put a pin there and figure out what goes here after division. Again, synthetic division is our superstar in this kind of problem. I would say you could expect it to work in most every single problem. There will be one exception, and we'll make a really big deal out of it once we get to that exception. We saw it as a quiz problem, essentially. So let's take the 2 that came from here, or the opposite of this 2 here, put it in a bracket. We have coefficients that go 1, 2, 5, negative 26. Sometimes if you see a large coefficient like negative 26, that was just put there and designed in a way to make it become 0 down below. So another synthetic division, a 1 will carry down to start, double it till we get a 2, tally, and we're up to 4. Next, double that 4 to get a value of 8. Add those together, and we're up to 13. Then double that, and miraculously, that's exactly 26. And we get a 0. If we didn't get a 0 here, there's a small mistake somewhere. That's an indication, backtrack, maybe check if their values are right here, or maybe just a simple arithmetic mistake inside this synthetic division is what happened. But from this stage, we'll say coefficients up here with x cubed, x squared, x, and then the constant term. If you divide by degree 1 polynomial, the new terms would be x squared, x, and then the constant term. In other words, we found information that plugs in right here. That deserves a color, I'd say. It'll be x squared plus 4x plus 13. So we've definitely factored g of x a good amount by taking out that x minus 2, but we need to factor it as a product of linear factors. In other words, that 2 right there needs to become a 1, and we're going to split this into 2 more factors multiplying together. Ordinarily, what we would hope is that this thing just factors nice. If it was, say, like a x squared plus 4x plus 4, that'd be terrific, right? You could take an x squared, let's just put this here as a side comment. This could factor as x plus 2 times x plus 2, equaling x plus 2 squared, if you prefer, slightly nicer format. So if I wanted to make this problem shorter on a real exam, that's probably what I would do, just make this factor right away. But this is the nasty one, so let's factor it the hard way. I don't see any great way to factor it directly, so we're going to find the zeros of this thing instead. So we're setting x squared plus 4x plus 13 equal to 0. To solve this thing, we're probably going to need the quadratic formula. I really don't see any other way to go with it. So let's start with the discriminant. B squared, try and go for a different color there. Discriminant will be b squared minus 4ac. And this is a good time to go to this polynomial, just read off coefficients. A is 1, B is 4, and C is 13. So plugging that in, we're going to get 4 squared minus 4 times 1 times 13. And that means this turns into 16 minus, oh geez, that's like a 52. So that would be negative 36. Don't forget you're allowed a calculator on the real exam. So some of this stuff you could just throw right into a calculator and that would be okay. So with a negative 36 here, we can now go and say the solution to that equation set equal to 0 is x equals negative b plus or minus the square root of the discriminant b squared minus 4ac. That just means negative 36 goes right in that slot. Then divide it by 2 times a, so that's just going to be a 2 times 1. And now that we've written that out, let's also, just for the sake of having stuff on this set of notes, it's meant to be notes, let's write this out as a formula generically. What we used is ax squared, plus bx plus c equals 0 by the quadratic formula. Let me fix that there. By the quadratic formula, the solution has to be x equals negative b plus or minus discriminant divide by 2a. Oh, but not like that. There we go. So we've got this so far by using that formula. Let's put in the remaining information. B is a 4, so this turns into a negative 4. Plus or minus. There is a negative in our root, so when you see a negative, we'll throw in an I. Take the root of 36, which is 6. I'll turn that into a 6i later. And whole thing is divided by 2. This kind of problem just keeps on going. When you divide it by 2, you can divide here to start. That's a negative 2. There'll be plus or minus. Divide by 2 here as well. Now we're forced to if you divide just one term in the numerator by 2. And this will be a 3i. So we found 2 more zeros of this function just by setting that equal to 0. But that means it will factor using these as the portions of the zeros. So let's go and write our official answer. G of x is equal to x minus 2. That one was just given to us. Then we take and write x minus the first solution that was here. This will be negative 2 plus 3i. And then x minus the conjugate of this one. We don't necessarily even need to look this up. Once you put this down once, and the fact that these are only real numbers for coefficients, the conjugate is going to be the very next factor you write in. So x minus negative 2 minus 3i. But the conjugate occurs right here, which is easy to get confused on because the signs are just so mixed up. Once you get to this step, though, this is the stopping point for this kind of problem. I definitely wouldn't worry about doing any kind of work inside these groups here. And definitely don't try to expand it all out. If you did, you would just go back to the original problem right at the top. But this problem is so long, let's put it in a box. That's our answer on this one. It's finally expressed as a product of linear factors because all the degrees on x are of degree 1. And that's what they were asking for. Any questions, folks, on this one? Okay, so that's possibly a problem that could be on exam 3, but again, if it is, the rest of the exam has to account for that and shorten up by a good amount. Probably have to take off a couple of problems. The final exam could also possibly involve this question right here. Final exam is a 2-hour exam, so longer questions can happen on those. But let's go take a look at the next one. Any questions or comments so far? Okay, so next one. We're now looking at the rational zeros theorem. The rational zeros theorem, I think we've mentioned before, this is a theorem that does show up on exams quite a lot. In ALEKS, it can be kind of a pain to get through these kinds of problems. But I'm not going to throw one that is like a really huge long list where we have to worry about duplicates so much. If you see this on an exam, it's probably going to be a pretty quick and direct kind of problem. So the way it goes is, it says, if you have a polynomial like this, and all the coefficients are integers, so no fractions, this would have to be like a 5, -12, something like that. And if P divided by Q, already reduced, is a rational zero of F, then P is a factor of the constant A naught, Q is a factor of the leading coefficient A sub n, and let's practice that right here on H of X. Honestly, it's a pretty fast problem, but this one's tricky to get just right. It does take practice to get it down really quickly. When you see a polynomial like this one, you could say match the color coding. And then write down P divided by Q. Let me get my colors going. Our answer is going to be pretty much right here, but we need to specify what is P, what is Q. Organization is the best way to start this thing out. So P itself has to divide our term. Oh, I think I got my color coding all mixed up. P has to divide this term, and that means this is really bad color coding. Let me see if I can fix that. Let's put P as green on the top, Q as blue in the bottom. It doesn't need extra noise. If we get the color coding right, it's not doing any favors for us. So P has to divide 3. That means P is going to be either positive or -1, positive or -3. Then we take a look at Q, has to divide the leading coefficient here. So values for Q could be positive or -1, positive or -2, positive or -4. So just anything that divides -4 would be a possibility for Q. Now we have 6 possibilities altogether, but 3 main ones, because of sign plus or minus, we just tack it on in front in this way. The next thing we do is, when I do this, usually just focus on one numerator at the time. Think of P as all of your numerators, Q as all of your denominators. So I have a plus or minus 1 divided by 1, which would be 1. Let me control Z that. Next one would be plus or minus 1 divided by 2. And then we just keep on repeating down the line. Next, plus or minus 1 divided by, now the last denominator 4 will go in. Then up at the top, we can change over and now use this as the numerator, and same exact process. It will even look the same for denominators. So just to help convey that pattern, let's go down below and say, next one is going to be plus or minus 3. Then plus or minus 3, but divide by the next denominator, which is 2. Then almost there, plus or minus 3, divide by still the next denominator. And this is the last one, which would be 4. Definitely double check if anything could reduce in that list. But again, for this kind of problem, it's going to be a really quick and direct one. These are the only possibilities for a fraction or rational number to be an actual zero of H of X. So if it has a rational zero, it's in that list. No guarantee it has any rational zeros though. Any questions, folks, on finishing off that one there? Okay. Again, the rational zero theorem problem is weird because its purpose is you get a random polynomial, you look at the list of zeros, and you start trying to factor it and find every other zero. But in our class, it's kind of a dead-end topic. We just use it and then stop. So if you know you're doing a lot of math, this theorem goes further, but we're just sort of moving on once we use it. So let's do that. Any questions before we move on? Okay, so next section is a conjugate zeros theorem. And this theorem is not so bad. It's essentially expressed in this way. If you have a complex number that's a 0, its conjugate is also a 0. That's the whole content of that theorem. But the nasty thing about that theorem is its use can come in lots of different formats. So we have just 3 different versions of how it could come into play. Let's practice all 3 and just see what they all look like. So this example 5 is a really quick one. We're just writing down a polynomial. It has to come out to degree 4. And here's 3 of those zeros. We want to leave it in factored form. You could expect that as part of the instructions, since no reason to take extra steps that aren't needed on an exam. So we'll start by going f of x equals, and the first factor will be x, and then something. Anyone see what goes in here to complete that first factor? Exactly. We go to the zeros that they gave us, flip around the sign, and then we're in good shape. So plus 2 here. They gave us another 0, positive 1. So we'll go x minus 1. And as you write these down, it's not a bad idea to check them out. If you did plug negative 2 right here, this would be 0 times negative 3 and something else to the right. That would cause the whole thing to go 0. Plug a 1 here, the whole thing, it goes to 0 as well. So we're definitely in the right track. Then the next one, they gave us a complex number, 3 minus I. Let's convert that to a bracket just to make it more visually readable. This will go x minus 3 minus I. But the moment you have one complex number, 0, you have another automatically. That's the whole content of the conjugate roots theorem. Next one is x minus 3 plus I. Then what I would do is check out the degree. I don't want to check it out by expanding all this and multiplying it through. We would never get through the exam if we did that. But if you look at this position, the x's in front of all those terms, if you did expand this out, your first step would be to take x times x times x times x. That would be x power 4, matching degree 4. So visually, this has the right degree. Then the whole problem is over. We just had to write down a polynomial. But if we didn't know of the conjugate roots theorem, this would be the factor that's really, really easy to leave off. And if we didn't check the degree, even easier to leave off on that thing. Well, that's one down so far. Any questions, folks, so far? Okay, so that's the really fast question for the conjugate zeros theorem. Example 6 says, find all other zeros of this p of x function, given that 2 minus 3i is a 0. This one is not so nice. This one takes a while to get through. So let's take our time right here. They gave us 1 0. That means we have 2 zeros really. And we can start by saying 2 minus 3i and 2 plus 3i are zeros of p of x. That means if we take x minus this one, x minus that one, we'll have a polynomial that does divide p of x as well. But that polynomial is of degree 2. This is where our synthetic process completely breaks down. We never even looked at what happens with a bigger synthetic division. So we'll use ordinary long division on this one. And I think this one was essentially our quiz. This is just a slightly different problem. So here's the next step. You have to take the 2 zeros that we know about and write out this. X minus 2 minus 3i, x minus 2 plus 3i, and that thing divides f of x. So to see what's really dividing f of x, we need to expand that out. So it starts by, first, we'll take x, distribute it through the next group. We'll get x squared minus x times 2 plus 3i. Then distribute 2 minus 3i through the group. Here to here, we get negative x, 2 minus 3i. And here to here, this converts to positive, 2 minus 3i times 2 plus 3i. So that's the first expansion on this thing. Then it's really not too bad after we've done this a few times. This is probably our 4th or 5th try on this kind of process. Any questions at the moment to that stage? Okay, pretty much all we're doing from here is expanding further, foiling over here, combining all like terms. And there's usually loads of cancellations. So starting this off, we have x squared minus 2x minus 3ix from distributing that negative x into the group. We'll do it again over here and get negative 2x plus 3ix. And this one is truly pretty fast. Let me know how you feel about this as a shortcut. we have a conjugate pair here. And every time we multiply FOIL out a conjugate pair, you get the 2 squared as a 4 plus the 3 squared, giving us a 9. And that's the whole punchline to those every time. But I'll leave it up to the class. Should we expand it just to see how it would go if we did go that route? Okay, let's expand it as well, just to visualize it. I'll do it in this orange pen and put the result right up here. Our goal is to see if we get a 4 plus 9 or a glorified 13. So first, here to here is going to give us a 4. Here to here will be plus 6i. Then change it around, distribute this way, that's a minus 6i. And then finally, here to here would be minus 9i squared. And then the next concept we need is that I squared. I squared equals -1. So that -9 is a glorified positive 9, really. And the whole thing turns into 4 plus 9, giving us a 13. All because of the middle two terms right here just canceling away. Honestly, on an exam, I would probably do it this way because it's just as fast as the shortcut right here. I would only do this if I've done it a million times and I just know for sure that this trick is not going to cause me any trouble. Any questions, folks, on the steps so far? Okay, so let's keep on going. Well, actually, we can start canceling things. Let's see. We have a -3ix, positive 3ix. So we have x squared. We have -2x twice, so minus 4x. And then the 4 plus 9 gives us a 13. And so that's our polynomial that divides, oh, is this a p of x? I said f of x here. Let me fix this. That's the polynomial that divides p of x. So now we have to really do that. We're trying to find all of the other zeros. And the only way we can do that is if we find the quotient after dividing p of x up here by that polynomial down below. So this is our long division go at this thing. Let's take that whole thing and write out this. Long division with x squared minus 4x plus 13 is dividing into the original function, x cubed minus 5x squared plus 17x minus 13. Okay, so now to start off, what we visualize is leading term right here being x squared, dividing into the leading term over here being our x cubed. So let's maybe put it on the margin just for some quick scratch work. So x cubed divided by x squared gives us a result of x, and we just copy that directly above. That makes sense, folks, on producing the x? Awesome. Once we have that x, we're going to produce a row of values right under here. Anyone see what they would come in as?
Are you asking to distribute the x?
Yeah, exactly. Yeah, I heard a x cubed. Exactly. Awesome. And one more. So we've got it. That's pretty much the process. There's one more step here before we get too far ahead of ourselves, but if you're that far, you're probably in really great shape on getting through the whole thing. Next thing you have to do is subtract polynomials. Some people visualize it this way. The negative is distributing through and you're subtracting in that way. If you visualize it that way, then I'd say that's a terrific way to show this kind of work. Usually I kind of make it a little bit of a mess and put my negative all throughout. Yeah, question first.
With 13x, would it be minus 13x since it's positive, but it's supposed to be the opposite sign?
Yeah. We could express it by putting a negative kind of like that.
Oh.
Or by just flipping all the signs. Yeah, exactly. So let's go with the route of flipping all signs. It gets messy though. That's the kind of downside about it. I'll put it the new sign kind of heavy and just circle the sign we're actually using. So if you go this route, it's messy, but it works. And again, some people like to go like this instead. This is implying you have a negative x cubed, positive 4x squared, minus 13x, if you prefer going that route. Looks cleaner, but there's a danger of just forgetting to flip a sign as you go through it. So let's go officially, kind of like this. Throw down a tally bar, and then start adding things up. We have a 0 here. Negative 5x squared plus 4x squared is going to give us negative x squared. Then here, 17x minus 13 of them will give us just 4x's. And then carry down minus 13. So that's one full process of the long division. And then looks like only one more step. We end the process the moment the degree down here is lower than the degree of the divisor in this location. When it's even, we still have one more step. But we still do this. Focus on the leading term here. Focus on the new leading term here. This time the scratch would be negative x squared being divided by x squared. Then this whole thing becomes a -1. So let's come up back above and go -1. Essentially, we're about done at this stage, but not completing the long division is not too wise because we want to see if we really get remainder 0. If we don't get remainder 0, that's kind of heartbreaking. It means there's a mistake somewhere in here, and those are hard to find. If this happens to you, definitely don't do this. Oh dear. Did you get negative x cubed plus 4x squared minus 13x? Yeah, so you have to flip the signs and below negative x squared plus 4x and then a minus 13. Yeah, and then our next step, we're going to take our -1, multiply it through. It'll be a negative x squared plus 4x minus 13. But then when we flip our signs, we should be getting a remainder 0. So I'll put this as positive minus positive. But now at this stage, all I've got is a 0 left over. You find it? Okay, gotcha. Other questions so far, folks? Okay, well, at this end stage right here, it's hard to know just what's going on next or what to do very next. But remember, our goal is to find all other zeros. That means this is a factor of the original function. You could set it to 0 right here, and you found all of the other zeros. You could take an additional step to write out p of x factors in a certain way, this times x minus 1. I think that's a lot of additional work for not getting to the main question, finding all the other zeros. I would probably end this whole question at this stage by going like this. Let's find a new color. Let's set that equal to 0. So x is now equal to 1. That didn't go long enough. And we can now say the zeros are. Notice I'm not directly answering the question they're asking us, but this is probably the best practice. When it said find all the other zeros, it's referring to, let's see, 2 plus 3i and a positive 1. But if you give me just all of them, there's no chance of getting the conclusion wrong. You have everything there. So I'm just going to state all of them. 2 minus 3i, 2 plus 3i, and positive 1. And you know, if you had extra time on this, you could use our remainder theorem to evaluate p of 1, see if it's really 0, or honestly, just plug a 1 right here. Let's check this out. If we checked p of 1, it would come in as a 1 minus 5 plus 17 minus 13, and, oh geez, what is that altogether? That would be a 4. I think that is actually a 0. I was getting a little nervous there for a moment. Let's say that this is a check. And this is our official answer. It provides more information, but that's okay. I probably wouldn't want to worry about getting the right ones in that list while doing the exam. I would just state them all. Any questions at all, folks, on that example 6? Okay, I forget which quiz this one was, but there's a very similar problem like this on a quiz as well. And just as a reminder, for a decent strategy for studying, if you get kind of done with some of these old documents and felt like you've gone through these enough, go through your old quizzes. Your quizzes are pretty much taking a final exam. All the questions are good, important questions, and writing them in as quizzes. That's literally what I've been doing with these kinds of things. These are really pretty decent final exam questions on their own, which means they're great exam 3 questions as well. But let's move on to the next one. We're still talking about the conjugate zeros theorem, but there's a lot of different ways to run a problem through that thing. And here's the last one, example 7. It says a polynomial function, p of x, has the following zeros. Now this time it's given as a table and also specifying multiplicities. It's also known leading coefficient of p of x is 1. That means when we go to write down the factorizations, nothing too exciting happens there. If it says 5 in here instead, you'll have to have a 5 times your very first group. Degree of p of x is 6. This will be like our check to see if we have the right function. And it says use this information to write p of x as a product of linear factors. So starting it off, we'll go p of x equals. On this one, we have a 0, 3. So we can begin by writing x minus 3. But this doesn't fully complete the group. Anyone see what's missing on this thing? Exactly. If it has multiplicity 2, then that means the 0, 3 came from a group to the power 2. Good call. So power 2 goes here. We'll probably find out something is missing once we look at that information here. We think, oh, geez, well, there's a multiplicity, just bump up a power until you hit degree 6. Then we'll go over to the next one. It'll be at x minus 4i. And you know what the tempting thing is to write is x plus 4i. Or excuse me, what I was going to say. It's tempting to write x minus 2i right here. I would say it's a really bad call. Let's go plus instead. Anyone see what should go right in this position? Good call, good call. We're using the conjugates theorem again. It looks weird because these complex numbers are of the form of 0 plus b times I. But you can still take their conjugate and go like this. If it's an x minus, they'll go to x plus, and then 4i right here. So now we're officially done with the 4i. We use the conjugate theorem in that location. Next, we'll do 2i. So x minus 2i. Then multiplying x plus 2i. And that finally finishes this thing off. Where the yellow is highlighted down here in the answer, that's just the use of conjugate roots theorem. Now let's double check the degree. We'll have power 2 on x coming from here, then power 3, or degree 4, degree 5, and then finally degree 6 altogether. We ran out of fingers. So that does look about right. Any questions at all, folks, on the end on this one? Okay, I like these kinds of questions. They're really fast and direct, and they are still highlighting important information about the problem. And keep in mind, there might be one question like this, but I'm not going to add a bunch of questions like this on the exam. So think of example 6 and example 3. This one was kind of nasty as well. Those are kind of the exceptionally little bit harder questions on the exam. I won't be loading the exam with the hardest questions. That'd be kind of awful. It'd be awful to grade as well. So after all that stuff, we get through section 5.5. That deserves a breather. I wanted to spend extra time on that section because it's the trickiest section in the whole course, really. And it's finally coming due on exam 3, so we spent that time. Well, we made it. This is not as bad. I'd say it's a much easier, but it's still tricky on its own. This is the big theorem where we just have to be familiar with what horizontal asymptotes look like. I directly copied this out of the notes. So these are old examples, just really fast ways to illustrate what should happen to horizontal asymptotes. Let's analyze this maybe one more time, just to get a warm up on this thing. On example 8, the degree of the numerator is 2, so numerator is higher of the degree than the denominator, which is of degree 1. So there is no horizontal asymptote. I'll use HASY for horizontal asymptote. This one has a tie on degrees, so take the coefficient of 4, coefficient of -5, and the horizontal asymptote would be y equals -4/5. Really a -5 down there, but I just scooted it in front of the fraction. That's a stylistic choice. You could put it wherever you'd like. Then on this next one, the degree of the denominator is 2, so it's the highest degree from numerator and denominator. Degree in the numerator is just 1. So this automatically has a horizontal asymptote of y equals 0. So that's the use of this theorem here. Now let's try it out on some of these problems down below. So example 11 says, we have some arbitrary rational function just thrown at us. We want the equations of the asymptotes, x and y intercepts, and then we'll sketch the graph using all that information. I think this is the trickiest one based off the quiz that we had for this section. So I'll spend a little bit extra time on getting the sketch just right. Very first thing I would probably do though is, let's go up here and fix this function. It's not in a great format. You could say that it's equal to, but we can't do anything about the denominator. X squared plus 1 does not factor. That's a sum of squares. You'd be able to factor it if you use complex numbers, but we don't get any actual asymptotes from that. So we're going to leave that one directly as is, x squared plus 1. There's no way for that even to equal to 0, so looks like no vertical asymptotes on this thing as well. The numerator does factor. Of these problems, I'm only going to give you things that factor nicely. I wouldn't involve a, say, quadratic formula in this concept. That's just too crazy of a question for an exam. This is about as hard as the factoring would be. It's not the nicest factoring, but it's not terrible. For 2x squared, you can split it as 2x and x. We can say try plus and minus because of the sign -3. And a prime of 3, that means you can put, say, a 3 here and a 1 here. Then definitely check it out. Multiplying this to this is -6x. This to this is positive x. Tally, and we get -5x, which means we hit our goal of -5x in the middle. That's enough evidence to say we have the right factorization already. So now that the function's fixed, we can run through part A, B, and C a little bit faster. I guess we didn't necessarily have to factor to get the asymptotes. We could say automatically the horizontal asymptote on this one is going to be y equals, anyone see what it should be in this problem? It would be 2 exactly. So the way to think of this one is the numerator is degree 2. Denominator is of degree 2. That means we have a tie. Then take coefficients from the highest degree in the numerator. The highest degree in the denominator has a coefficient of 1, so we can ignore that. We're just dividing by 1. Let me write out this way just to show the process a little bit better. It's y equals 2 over 1, or y equals 1, or let me try again. I divided a little bit incorrectly there. Y equals 2 is the horizontal asymptote on this equation. Now, x squared plus 1, if you even try to solve that, you'd set it to 0, get x squared is -1, square root both sides, and x is the square root of -1, either positive or negative. So x equals -I or positive I. That doesn't help us at all. This is pretty much just telling us no vertical asymptote. There is no real number you can plug in there to obtain a 0. You have to use complex value numbers. So let's say here, vertical asymptote, none. That means this function is kind of unusual. We usually have a vertical asymptote. This one is more special, I guess. Any questions, folks, with getting through asymptotes? Okay, next thing we'll take a look at are y-intercepts and x-intercepts. X-intercepts are not too bad. For this process, all you're really going to do is take r of x and set it to 0. But the only possible way a fraction equals 0 is if its numerator is 0. So then we just pull off the numerator, 2x plus 1, x minus 3, set that to 0. Now we have a factored form to set to 0. This would imply immediately either the first factor is 0 or the second factor is 0. And here's our solutions finally. On the first equation, it's -1, then divide by 2. And on the second equation, x would be +3. So the x-intercepts would be -1/2 and 0. And the next one would be 3 and 0. So that's the intercepts in the problem. You're really just looking at your numerator. That's why it's a good idea to factor them right away. You're going to have to eventually, somehow, some way, at some point. And from the factored form, you almost immediately get these values. In fact, if you just look at this, imagine setting it to 0, subtract 1, divide by 2, that's your x-intercept. You can just eyeball this thing. Put in 3, you would get a 0, so that's your next intercept. And the y-intercept is pretty quick too. What we do for the y-intercept is we, as a process, go r of 0 and find a value. At a y-intercept, x is 0, so we just plug 0 here, which means we're plugging 0 into all the positions of x up here. It'll be a 1 times -3. So everywhere I had an x, I'm just imagining now it's a 0. So I just pulled in a 1, just pulled in a -3 from here. Down below, it's just going to be a 0 plus 1. So we can ignore it. The whole thing turns into a -3. And this tells us that the y-intercept, let me fix that first, is going to be 0 for the x-coordinate, -3 for the y-coordinate. Well, that was our intercept so far. Now we're ready to sketch this whole thing. Any questions so far, folks, to this stage? Okay, let me grab some of this stuff that we might need. Probably right here should be enough. And now let's imagine you're sketching this in an exam setting. What should that sketch even look like? It doesn't have to be perfect. It doesn't have to have immaculate information on it. It's just, it has to be good enough. So let me show you what I mean by that. First thing I would probably want to do is, well, let's put down a axis. That's definitely the first thing to do. That I was trying not to scroll up, but we need to remind ourselves we have a horizontal asymptote, y = 2, but no vertical asymptotes. So let's start with the y = 2. So let's go up 1, 2. Here's our horizontal line going through. And y = 2. The no vertical asymptotes definitely feels weird, but that can happen. So we'll just run with it and see what happens next. Let's put down our x-intercepts. We have one at -1/2 and 0. So here's, oh, let me fix that, -1. And here's our first x-intercept. Right about there. Next one is at 3, 0. So we intersect the x-axis in this location. And for the y-intercept, that was at -3. So down 1, 2, 3. Now we have to sketch the function based off this information, but the trouble is we don't necessarily know if the function is above or below this asymptote. We just know it's approaching it. So if you're doing this on a real exam situation, all you really need to do is evaluate at, let's say, one more point on the left, one more point on the right, just to see where the function is. Even if it did something weird and actually flipped on you, I would still take your answer as full credit. And when I write these equations, I do graph them first and make sure there's no weird, crazy stuff that's going on that you would need a graph to make sure you're doing it just right. If you follow your nose on these problems, you are going to get the right graph. So let's see what happens. We're plugging in a -2 inside the r of x function. So let's evaluate r at -2 to start. I'm just going to throw it into the factors. That's the fastest way to calculate this. That would be -4 plus 1, so -3. Here, this is going to be a -5. The -2 squared is +4, plus 1 gives us a +5. And let's simplify this. It's positive, 5's divide, and you'll just get a 3 altogether. So at -2, we're at height 3. So we are up here in this problem. That's interesting. It looks like it comes in around. It has to go through, down, and it looks like it comes up. I don't know if it comes up around or stays down below. We can evaluate one more time and just get a feel for it. But wherever that point lands, we'll just do our best we can with the sketch that we see based off the points that are there. So this next one is r at 4. So we're plugging 4 here. That'll be an 8 plus 1 for a 9 to start. 4 in this location is 4 minus 3, so just a positive 1. 4 down here, that will be 4 squared for 16, plus 1, we're at 17. So 9/17. That's really close to a half. It would be if it was 9/18. So at 9/17 for 4, we're about here. We probably expected that because we did have an x-intercept right in this location. That's now based off all these points, this is my attempt at the sketch. I'll start off really close to the asymptote, climb just to reach that point, but then dive, come up around, go through, and you don't have to do an evaluation at 5, 7, 8. Just do what seems natural. I'll let it head towards the asymptote, and I would accept that for full credit. And like I said, I designed these problems so that if you're plotting them in this exact way, you will have the right sketch. I eliminate the problems where maybe it did come up above and then settle down. We wouldn't be able to even find that on a real exam unless we had loads of extra time. So that does it. That's really all that's expected on the sketch. And the confusing part of this whole process is getting that point and that point to get the entire curve. Any questions at all, folks, on the conclusion here? Okay, so that's one down. Let's try this again since rational functions are absolutely kind of confusing. This one's kind of a standard question you might see on the final exam, but I've seen this type of question on the final exam as well, example 12. So on our exam 3 that's upcoming, if I decide that the exam is a little too long, I might ask example 12 instead of the one we just did. That's the same kind of content, but we are not focusing as much as this on the nitty-gritty algebra. So this is an attempt to make the question a little bit shorter. So let's try this one out. It says, sketch the graph of a rational function f that has all of the following properties. We'll have a horizontal asymptote, 2 vertical asymptotes. We have some function evaluations. This is the doozy on this one. We have to do a sketch that obeys a range of -3 to positive infinity. So our graph is at lowest -3, whatever we sketch. There is more than one correct answer to this. So anything you draw that just hits all 4 bullet points all at the same time and passes the vertical line test will be considered a valid answer to this problem. So if you see this question, then we decide our rational function topic is just focusing on that kind of information. It's still tricky, but it's faster at least. So I'd probably start off just by going like this. I think on our real exam, I get in the habit of printing these out, so it'll just be provided. Now it has a horizontal asymptote at -3, so we can start by going down 3. Throw in a dashed line. You don't have to say y equals -3, but it's usually pretty good for the notes, a decent habit to get into. Now vertical asymptotes at -3 and +5, so left 3. And then draw a vertical line. And next, at +5, draw another dashed vertical line. So that's the grid lines of this whole problem so far. And notice when it says the range is -3 to infinity, that means our curve cannot be down here at all. It can possibly even not necessarily be anywhere near -3, but because it's a horizontal asymptote, on the ends, it's going to be approaching that height. So now we just have to draw a graph that's going to obey those asymptotes and also have these function values. So let's just plot the points down from that information. It says f of 6 is 0, so we have an x-intercept right over here at 6. F of -5 is also 0, so here's -4, -5. And f at 0 is 3. That's going to be our y-intercept. So now we just have to complete the sketch. Now, when you go to draw the overall curve to this thing, we do have to be a little bit careful because once again, if you did a curve that did something like this, I'm going to delete it in a moment. that might be plausible, but then we violated the range on this thing. It looks like the range would be involving values going down to negative infinity. So we can't quite go like that. And we can't necessarily do something that goes, say, like this either. We've crossed through a vertical asymptote. Those are real honest barriers on a function. It can never cross a vertical asymptote. Horizontal asymptotes are a little bit more accepting of that kind of thing. So we have to make sure our curve goes like this on this problem. So that takes care of that portion. Next, here, there's a lot of different things you might try. And it's common to see a graph that goes like this. But again, that wouldn't be correct on this problem. We have the wrong range. So you could do something just really, really basic if you wanted. Make it come through like that. Let me try again. So that would fit the bill. We have the curve obeying the vertical asymptote on the left and the right, and it goes through the y-intercept. The last thing is kind of the same as before, just make it approach vertical asymptote as it's going to the left, approach the horizontal asymptote as it's approaching to the right, and that's a whole curve. There's not too many different variations on this, but again, if you got a curve that at least does something like this, your curve would be a lot different, but still obeys all the properties. That's an acceptable answer as well. Any questions at all, folks, on getting through this one? Okay, again, sometimes this one appears on the final exam. That's the only reason I got in a habit of sometimes putting this on a review. So I may not ask it on exam 3, but knowing how to work this problem in this direction is still important information. Well, let's see what we've got next. There's about 9 more minutes left. So I'll leave it up to the class. We can try one more rational function for just extra practice on that topic, or start looking at inverse functions next. Any volunteers for a direction to go next? A function inverse or a rational function? Let's try an inverse. We're still doing a rational function if we do that. Here's the function right there we're about to invert. And this is the information about inverses. I'd say the biggest takeaway about the notes up here is that you can test that you have an inverse by doing the evaluation and getting an x here and here. But if the instructions say find f inverse, it might not be as wonderful as a formula. It's not telling you how to actually find it, unfortunately. So to find the inverse, here's what we'll do. We start with the original function up here. We can call it y equals f of x, just to place down our next variable that we'd like to work with. Then let's input the actual function. F of x is 3 minus 2x. Divide by 7 plus x. And let me drop this down. I'm suddenly not thinking I'm going to finish this on that one page. Then from here, the next big step, which is the whole punchline to inverse functions, is we change the role of x and y. We completely swap them. So x swaps with y. Now on the left-hand side, it's x equals, and the right-hand side, it's 3 minus 2y, divide by 7 plus y. And this algebra is kind of weird, but the more you do this specific problem here, the faster and more easy it is to get through. If you're solving an equation for y, we must clear the denominator right away. So visualize it this way. You're multiplying by 7 plus y on the right-hand side, just cancels it off. You have to multiply it on the left-hand side, so it's just half of a cross product. X times 7 plus y, the document scrolled for no apparent reason, is equal to 3 minus 2y. So we've eliminated the denominator. Now we can expand x because we have to get this y variable freed up. So distribute 7x plus xy equals 3 minus 2y. And if our goal is to solve for y, we need to get y in one spot. So here's our next steps. Let's eliminate the 7x. I'm thinking about putting y on the left-hand side now, if we take that step. On the right-hand side, let's add 2y. And our new equation becomes, let's take a look. So 0 on this column. These are not like terms, so it's just xy plus 2y equals Then over here, 3 minus 7x. So now y is on one side of the equation. We can get in one spot by factoring it and get y times x plus 2 equals 3 minus 7x. We're basically home free at this stage. Just divide by x plus 2. Y equals 3 minus 7x. Divide by x plus 2. And we've done it. We've inverted this original function way up the top here. It's still a good call, but I never take off points for this. It's the true inverse function. Sorry, go ahead. They do actually. 3 minus 7x, just a change there, and an x plus 2 rather than an x plus 7. There's a formula for this kind of stuff. So what people sometimes do is, if you invert rational functions for the living, you could write f of x equals a plus bx, c plus dx. If you invert that function, you have a formula for this right here. So there's definitely a pattern of how these really invert. But sometimes the formula is worse than the process. That's why the book never even tries to go into that for this particular problem. But other questions or comments so far? Okay, well, what we've had so far is f inverse at x is 3 minus 7x. Divide by x plus 2. And let's see, what did they want? They just wanted the inverse. So we got it, it's right there. If you left it in this format, that's still the inverse 2, that's acceptable. Then it says for part B, state the domain and range of f. This is the harder question. Not that it's a lot of steps or super technical, but it's a tiny bit confusing if we haven't done this a whole lot. It's not hard to get the domain of that function. Oh, I said of f. Let me do a quick revision here. I think my intention was not for f, but for f inverse. Sorry for that really fast edit there. We want domain and range of f inverse would be the question I would really ask on an actual exam. So we can get the domain of that thing. X just cannot be -2. So let's write out just to connect the thought. Take x plus 2 from that denominator, set to 0, and x is -2, but that's the excluded value. So we say next, domain f inverse. Let me make that inverse look like a real inverse. Is from -infinity up to -2, union -2, then go off to positive infinity. We've got domain on that thing. And to get the range on this thing, you could plot it, but that's not a fun process, right? Another thing you could do instead is go up here and find the domain of that function. Let's do it right up here. We can say, in green, take that denominator, 7 plus x, set it to 0. X would be equal to -7. So that's the excluded value for the original function up here. So we know that the domain of the original function f is -infinity to -7, union -7 to positive infinity. And that's exactly what we need down below here. We really have the range. It's the domain of the original function. So here's where that sneaky little equation comes in once again. The range of f inverse is ordinarily pretty hard to calculate, but because we inverted a function, we're just taking the domain of that function f, and it is from -infinity to -7, union -7 to positive infinity. I did want to put one comment here, which is a slick way of finding the range sometimes. Notice that this is a rational function for sure, right? It has a horizontal asymptote. Once that pencil gets caught up, I don't know why, but the pencil tool lags really badly. So the horizontal asymptote on this function would be -7 divided by 1. Y equals -7. And that's the value that's not in the range. So sometimes that works out really nicely. And the reason I haven't done that very often is your function can cross a horizontal asymptote, and then that idea breaks down. So if you ever cross a horizontal asymptote, this becomes useless. But it's still a good idea to look at your range, think of the horizontal asymptote, because when they do match up, that's a pretty good evidence you're on the right track. Well, any last questions, folks, on getting through this function inverse? Okay, I would say for inverse functions like this, the domain and range information is a pretty common next question to ask. And it's always these sort of tricks. The domain of the inverse, or excuse me, the range of the inverse is the domain of the original, and so on. Well, have a great day, folks. I think this is a good stopping point for us. We got pretty far into the notes, and then, like I mentioned, I will solve them all and have them uploaded probably pretty soon, around Friday at some point. If you're studying over this weekend and you are working and you have any questions, just like on the other exams, please don't hesitate to email. I'll be happy to help out. Otherwise, I'll see you folks on Tuesday, and we'll get through our third exam.